Welcome to The Quantum State, a podcast exploring the latest research and innovation in quantum computing. Join us as we dive into groundbreaking breakthroughs, trends, and news shaping the quantum landscape. Discover the cutting-edge developments pushing the boundaries of computing technology. Through insightful discussions, expert interviews, and in-depth analysis, we unravel the intricate theories and real-world applications driving this transformative field. The Quantum State also offers updates from BTQ, sharing the company's research progress and innovative products at the forefront of quantum computing. So, embark on this mind-bending journey with us as we navigate the realm of quantum computing, witnessing its potential to revolutionize our world. Welcome back to the Quantum State. Today, we have Peter Rohde and Gavin Brennan with us, and we're going to have a discussion just between the three of us about the landscape of quantum cryptography. Now, the main question that we get a lot of the time is what quantum computers will break in terms of encryption and how we'll mitigate that threat. So first, we really want to start talking a little bit about the quantum computing revolution in general. And so let's go around and maybe, Peter, you want to kick it off. Can you explain in layman's terms what a quantum computer is and how it differs from classical computers?
Right. So unfortunately, it's one of these things where any layman's definition gets it incorrect because even most expert definitions are very nuanced and get it incorrect. So it's worth talking about some of the properties that quantum computing exploits. And these are the ones that are unique to quantum mechanics, specifically things like superpositions, whereby something can have multiple states or values at the same time. A ball can be here or here in the normal world, but in the quantum world, an atom or another quantum particle can be here and here at the same time. So these unique differences between classical and quantum physics also give us unique ways of implementing algorithms that are built on top of those systems. So at the lowest level, a quantum computer is one that actively takes advantage of the unique phenomena associated with quantum physics and finds a way of converting that into some sort of computational advantage, a faster algorithm of some sort. Now, the way in which those algorithms actually work underneath, that doesn't have a single answer. That varies depending upon the algorithm, because there are different quantum algorithms that operate off very, very different principles upon which they're based. But all of them have this one thing in common, that they're trying to take advantage of the fact that a quantum system has unique properties like superpositions and entanglement, and a quantum computer is one that converts that into some type of benefit.
Gavin, anything to add?
No, I think Peter summarized it quite nicely. We now have a really good notion of what's called universality for quantum computers. So we know that there's like a minimum set of gates you need in order to be able to do an arbitrary quantum computation, just like there's a minimum set of gates you need in a classical computer, like NAND gates, to do an arbitrary classical computation. And yeah, it's, I mean, these really the essential ingredients have been known for quite some time, since the mid-90s, but only now are we really starting to see significant progress in the development.
Yeah, I think one of the most annoying things about, well, why I started writing my blog when I was in graduate school is because there was this big gap between the pop science and the research papers, where the pop science was like, it just does everything in parallel all at once. And it was just such bad intuition. And people still come to me these days talking about, quantum computers can just do everything at once. Then you start digging into the nuance, right? There's some algorithms that do an exponential speed up, some do a quadratic speed up. And you're like, well, if it does everything at once, how is this even possible? So building that intuition kind of in the mid ground is something that's really important, I think, right now for industry and for everyone to do to really truly understand. And I think what a lot of people also don't know until they start getting deeper into the field is that there's only a certain set of problems that quantum computers can be better at. And we talk about a few of them.
That's exactly right. People often think that quantum computers magically speed up everything, and that's absolutely not the case. It's very much the case that actually, of all the algorithms that we know, the ones where quantum computers provide an advantage is a very, very small fraction of the other known algorithms that we use. So you'll probably never see it in your desktop, even if the technology existed, just because desktop applications don't even have an application for lots of these things.
Yeah, I think my first blog post was called, "When can I play video games on my quantum computer?" Because that was the question I got all the time. And I was like, I mean, like, maybe you could one day. It's not going to be very useful.
Well, people ask me the same all the time. They want to know how good the graphics are going to be. Well, unfortunately, those algorithms aren't ones where we have any known quantum speed up.
Yeah. So going into deeper into the algorithms themselves. The algorithms that we do have, though, are very useful optimization problems, simulation, fundamental physics, materials. So what benefits can quantum computing bring to fields like medicine, energy, and materials?
Yeah, so one of the big promises with quantum computers is using them to model quantum systems. And actually, this was the original motivation of Richard Feynman's abstract model for a quantum computer. That's, you know, once you get just a small number of quantum particles, it soon becomes virtually impossible to accurately model it on a classical computer. So, for example, like, you know, even describing the physics of a dozen or a few more electrons in a confined two-dimensional region is reaching the limits of what you can do with a classical computer. So things just increase exponentially with the number of particles that are quantum. So yeah, you know, when people design drugs, you know, they're having to guess at the kinds of molecules that will be stable and that will, you know, provide the right kind of properties that they're looking for. Same thing with material design, or, you know, things like one of the big promised applications of quantum algorithms is to solve the nitrogen fixation problem. So find a more efficient way to produce fertilizer, because that's a very energy intensive application. I think it uses something like 3% of the world's energy is devoted to the activity of fertilizer production. So if you can find a more efficient way to do this, that would be great, but it's just very hard for classical computers. And so if you could kind of wire up the interactions that would mimic the physics you want to study or the quantum chemistry you want to study, then that's a great application for quantum computers.
Yeah, I was looking at, I think, the Cirque documentation, and they were saying, so on their simulator, you could simulate up to 32 qubits, I believe, and that uses 8 gigabytes of RAM. And just to have this kind of notion of how quickly it scales, for every additional qubit, you have to double the amount of RAM. So very, very quickly, it just becomes absolutely untenable as a calculation.
Yeah.
Yep.
Absolutely.
Exactly right.
But yeah, one thing I do want to add, though, is that, I mean, right now we kind of have a view that quantum algorithms will be good for quantum chemistry and maybe for finance. But, you know, we learned with classical computers that we really didn't know what they were good for until we had them. Like, for example, the field of chaos really wouldn't have developed at all without big classical computers. I mean, it was just kind of, you know, phenomenon that was discovered by numerical experiments. And it could be that when people start playing around with quantum computers, they'll find completely new applications. Maybe there'll be new kind of game theory scenarios that rise that you just don't get classically. And yeah, so I'm hopeful about that.
I feel like that's almost guaranteed that we're going to find so many more applications once more people have access to it and understand it. And part of the goal of these podcasts and other content is to get more people from outside of quantum into the field and actually saying what potential problems can be quantified.
Yeah. It could also potentially work the other way around too, that lots of the potential applications that we've identified today will end up not being as fruitful as we might expect, because it's important to remember that contrary to common belief, quantum computers don't just spontaneously solve things. They also take time to run things, just on certain applications a lot less. But it costs a lot more, inevitably, to use quantum hardware, no matter what point in the future it will be. So there'll be trade-off questions. There'll be many applications where a classical algorithm, even if it's an approximation that isn't perfect, on a cost-benefit analysis, it might be better to use good classical heuristics rather than go brute force with a perfect quantum solution. Those are trade-offs that are hard to know.
And for investors, of course, we have to give them some sort of hope for a better future very quickly. And quantum chemistry and finance applications are the ones that people talk about the most, because they're I think also a little bit easiest to visualize and have such a grand impact. But yeah, we can't know, right? All the newspapers back in the day that said, why would anyone need a personal computer in their house? Just not needed.
Exactly.
Yeah, and even now people say that, right? And I say that, right? Like, oh, you're not going to need a quantum computer in your house. And I hope to be proven wrong.
Well, that's right. If anybody says the future market for quantum computers globally is 8, then they're probably repeating history in the wrong way.
Exactly. So now that we talked about the applications of quantum computing, it is a really exciting field, and there's so much that could potentially be done, and people are building these systems. There is, and I think this is a great conversation to have during this time as we talk about kind of the ethics of generative AI, intellectual property, what are humans going to do when the AI takes over, to talk about, I'm seeing a lot of people there talking about, like, we need to shut down all AI development. And I think I've heard this a little bit over the last few years, but I wonder if it's going to become more common because quantum computers can also break encryption. And that's obviously a huge issue for the world. So let's dive a little bit deeper into that and talk about what are the main cybersecurity threats posed by quantum computing?
So really the big one is public key cryptography, and it's worth prefacing this with just some definitions about the different types of cryptography, because it's definitely not the case that quantum computers crack all cryptography. There's no reason to believe that. It's very specifically public key cryptography, and that in public key cryptography, also called asymmetric cryptography, the idea is there are 2 keys. One is a public key that can only be used for encrypting information, and another one which is a private key that can only be used for decrypting information. And that type of encryption is particularly useful on things like the internet, because you may need to communicate with someone that you haven't met before. So you take their public key and use it to send them a message which they can decrypt. The public key encryption systems that we use today are vulnerable to future quantum attack. But the other type of encryption is private key cryptography, where you have just one key that's used for both encryption and decryption. So you can't publish one of the keys publicly like you can with public key encryption. You instead have to find some way of meeting in a dark back alley where nobody can oversee what you're doing and share this secret key. So it's more restricted in what it can do, but that type of encryption, to the best of our understanding, is secure against quantum computers. And it's specifically public key cryptography. But that is a particularly big problem because it's the most useful type of cryptography for the reasons just mentioned, that you can use it to interact with people that you haven't had the chance to meet in advance. And of course, that's essential for making the internet work.
Yeah, I think that's a big point. So AES is one of the examples of the symmetric cryptography that you mentioned, and it is weakened, right? So it cuts kind of the equivalent key size in half. So if you double it, it should be about the same security. But that's a
That's right.
misconception I hear all the time as well, is people saying, well, we're just going to move everything to AES. But the applications of that are just not there. We still do need this private public key cryptography in the world to make our internet run as it does.
That's right. And exactly that same criticism that you just raised, that also applies to the people who say, don't worry about quantum computers breaking encryption because quantum cryptography will save us. Well, actually, quantum cryptography only solves perfectly the symmetric key problem. It doesn't actually provide a solution at all to public key cryptography and doesn't address any aspect of that issue or provide a solution to it.
Not to mention all the hardware that you need.
Well, that's right. It's hugely expensive, yeah.
Gavin, any other thoughts on your end?
Oh, yeah. So, just a comment that we know there's an interesting sort of competition going on with classical versus quantum on the cryptography side. So, in response to the quantum computing attacks on public key cryptography, there are these classical post-quantum cryptographic algorithms that have been developed. And you know, those are assumed to be immune to quantum computer attacks, largely because people just haven't come up with attacks that work. But that doesn't mean that we might not come up with such attacks. And the number of people in the world who are qualified in cryptography and also quantum computing that can actually test out these ideas, particularly without access to a quantum computer, just doing things on pen and paper, are very few. So, you know, a lot of the security we assume with post-quantum cryptography is based on some solid arguments, but then again, there's not a huge community of people that have really tried to attack it from a quantum attack side.
Yes, it's very much security based on the assumption that nobody has broken it yet, so it must be secure, which is about as weak as a security proof can be.
Yeah.
I always say I believe in human ingenuity. We figured out a lot of we've made sand basically think, so we'll probably figure something out. Maybe not tomorrow or next year, but I think humans will be able to figure it out at some point.
It seems so. I mean, there have been quite a few contenders for this post-quantum cryptography that Gavin mentioned, and it would be surprising if none of them had any legitimacy. But it does take time to figure these things out because it's not so straightforward that you can just prove that cryptography is secure. Really, the ultimate test is subject it to pressure, let people attack it, and if over time they don't find a solution, you might have some confidence.
Yeah, actually, something I think could be really interesting is maybe the post-quantum crypto won't be directly attackable by a quantum computer, but there might be side channel attacks you could do, which could be assisted by quantum computers. So, you know, for example, well, just a story I came across. I was talking to someone who managed to steal a Bitcoin from someone who was reusing their public key, and the patterns of the timing and lag for replies on the processing of that digital signature leaked out enough information that because the person was repeatedly using their public key, they could use some of the timing information to actually perform an attack, which allowed them to infer the private key and steal the Bitcoin, which they did return to the owner, but they just wanted to demonstrate it was possible to do. So that's like what's called a side channel attack, where it's not actually directly attacking the encryption from a information security point of view, but it's making use of imperfect implementations of the cryptography. Actually, you know, RSA also managed to do this. I think they were able to crack their own cryptography based on a side channel attack of an ATM machine. So, you know, it might be that there could be side channel attacks where if you just used classical processing, it would be still too hard to crack, but maybe with quantum processing, you could. That would be an interesting scenario where it wouldn't be a direct attack, but it would sort of be an indirect attack on post-quantum cryptography.
Honestly, the more I read about security, the more terrified I get, because there's always these articles coming out saying, oh, someone managed to identify someone based on like the cycles on their phone plus the typing and how that typing interacted with, you know, other components in their computer to create a fingerprint that was able to then break some encryption. It's pretty nuts.
It is an interesting point that you raised, because security goes much further than cryptography, and many people will sort of conflate the two and treat them as one and the same, whereas cryptography just refers to a piece of code that executes an algorithm that performs the transformations associated with encrypting something. But that's built inside some physical device, and people tend to completely forget that that's actually the weakest part in the whole thing. There are so many ways in which you can measure and interfere with the device implementing the algorithm that the algorithm itself isn't actually the thing that needs most consideration. That's probably incredibly robust and well studied. It's all of the implementation details that can't be standardized and made uniform and well studied.
I'd argue the weakest physical element is the people, us. In the entire chain.
Oh yeah, there's always like the $10 wrench attack.
That's right, the hammer attack. Give me your money.
Yeah.
Exactly. Yeah, I was thinking about the biometrics recently, and I was thinking about the was it the Avengers movie where they had to get the something, and it was a biometrics thing, so they went and just kind of got the eye out of the guy and pulled it out and used that, right? So that's the easiest attack rather than breaking the encryption.
Yeah.
But yeah, going back to let's talk about the differences in speed when comparing the classical computers to quantum ones. We talked about some exponential algorithms, some quadratic, but in breaking RSA keys, what are the speeds we're looking at today versus what a quantum computer could possibly do?
That's a very good question, because there it also comes down to implementation details. So on the classical side, when it comes to breaking RSA, for example, we know what the best known classical algorithm is. There's the general number field sieve, and perhaps there are some enhanced versions of that in the meantime. But we know from the way those algorithms are defined what the scaling is, how many compute cycles are needed to solve a problem of a given size. So whatever that number happens to be, the important point is that it's huge and therefore impractical. On quantum computers, it's the same thing. We also know in principle what that scaling relationship is, but it's a much more natural one. Putting exact numbers to it, that's where it becomes hard, because especially with quantum computers, it's not just that algorithm definition that determines the scaling. It's the entire architecture that implements it. And the vast majority of any future large-scale quantum computer is not qubits that are implementing the algorithm itself. It's ones that are dedicated to the error protection needed to keep quantum computers robust from decoherence or noise from the environment. So 99 point whatever percent of a future quantum computer isn't going to be working on the algorithm. It'll be working on protecting itself against noise. And those overheads, which are so dominant, vary enormously depending upon physical architecture, whether it's photonic or atomic, or whatever the case may be. Depends on what the noise rates are, which determines how much error correction overhead you need. So these numbers are not easy to put a number on. Really, when we theoretical physicists talk about this, we primarily make one distinction, which is that curve defining that trade-off. Is it exponential, or is it quadratic, or is it linear? If it's quadratic or linear, that's sensible. If it's exponential, it's not sensible. And that's usually the sort of definition that people in the field go and use.
Yeah, and on top of that, you know, I'm coming from the hardware side. So a lot of people also don't understand. You look at coherence times, or the time that information is stored in a quantum system, and you compare, say, a superconducting system to a trapped ion system, and trapped ions have much longer coherence times. However, the gate times are much longer as well. So when you're looking at actually running the algorithms and how that works, that scaling also is not one-to-one, and you have to look at many parameters to truly understand how much time it would take.
Exactly.
Yeah, I mean, we do have some estimates. So, for example, to crack RSA with a key of 2048 bits on a classical computer, that's something like, I think, if it's just like a desktop machine, it's something like 100 trillion years estimates. And of course, with a supercomputer, you could reduce that by maybe a factor of 1 million. But it's still completely inconceivable, barring some faster classical algorithm to factor. But on a quantum computer, using like a superconducting device architecture, which has a clock speed of around 66 megahertz, you could do it in a few hours. So now, you know, that assumes that we get machines that are quantum computers that are big enough to do that. And it will take, you know, 1 million or more, or probably more than 1 million qubits to do that. There are some ideas on how to bring that number down, but it's going to be in the several 100,000 qubits, at least. And we're certainly nowhere near that now. The current prototype devices are in the hundreds of qubit range, so we're quite far away from that. But yeah, I mean, it is a dramatic enough speed up that we have a real race going on.
And we're attacking it from both sides, right? So there's the hardware folks that are scaling it up on the qubit side, but there's also the error correction folks that are working on reducing counts on their end. So it's kind of flattening that way, both ways. So that's what's becoming kind of scary.
Yeah. Yeah.
And both of those play very important roles, both the software and the hardware. I think hardware tends to get a lot more coverage and emphasis in the media, but as you say, software is just important, because if you find a way to reduce the amount of overhead associated with correcting errors, boom, like you've saved a huge amount of work.
Yeah, but I believe there was a paper recently released where it was something like a 2 orders of magnitude reduction. I think it was 126,000 qubits. Gavin, you talked about it on another episode, I believe. And that's a big improvement in a decade of time. And
yeah,
even, yep.
Yeah, that's right.
So, I mean, so we're talking about a few hours, right? So assuming, you know, a quantum computer comes out tomorrow, everything's destroyed, everyone's panicking. Let's say a bank is for some reason ready and to deploy new encryption. So resetting passwords is kind of just a minor inconvenience, right? So I'm imagining this quantum computer happens, we're ready with post-quantum cryptography, maybe it's already been implemented, and everyone gets an email saying like, we've reset your password, we're using new encryption now, go and fix that, and everything's kind of fine. But there's larger concerns with this quantum crackable encryption, especially for sensitive data or national security. So there are, I assume there are, and I've heard whispers of it, right? That countries are collecting a lot of data that could be fundamental to national security and waiting for the day that a quantum computer can come about.
Store now, crack later. Absolutely.
Yeah. Do you all see that in the field? Do you all talk about that? Are companies concerned?
Well, I mean, this is just like, obviously, nobody's going to admit to doing sort of data harvesting in that way, but you take for granted that they do, because signals intelligence agencies would be crazy not to if they understood this interplay between encryption and quantum computers. So inevitably, it's the case that they are. The real question is, which parts of that data are actually at threat? Because not every piece of data that's encrypted using public key encryption and could in principle be cracked in the future will actually have value in the future. It would only make sense to do that if that information had forward value. Now, when you make a bank transaction, sure, you exchange keys with the bank to make a secure communication. But once that transaction is made, those records don't matter anymore because it's stored on their computer and it has no value if it can be intercepted 10 years later. But of course, if it's talking about secret agents being planted somewhere and it's really top secret stuff, it could very well have long-term forward value. And so the question to ask here is always, well, first of all, yes, people are going to be scooping up all the data to crack it later, but they're only going to be doing that if there's a reason to do it. Not every piece of information has that kind of value.
Yeah, I think like some examples of information that you might worry about being compromised outside of national security issues are things like medical records or insurance contracts, wills, so kinds of things which have a longevity, but you don't want people to know that information. That's definitely a concern, and I think, well, I don't know. I mean, I know some of the consulting firms are certainly recommending that healthcare providers and insurance companies do think seriously about upgrading their cryptography to post-quantum safe. But honestly, I don't know how responsive the companies have been.
I mean, the answer is probably on balance, not very responsive, because if you look at data security practices today, it's already pretty hideous. I mean, the number of data leaks you see, just practices aren't good. Most people, you wouldn't expect them to be on top of these trends.
Yeah.
Well, definitely there's, some people that argue that we'll never get to a big enough quantum computer that Shor's algorithm will work. A lot of people working in the quantum field obviously debate that, but there's a growing contingent, or there's a small contingent that says, it'll just never happen. But that doesn't erase the fact that governments right now, I mean, in the US, there's been announcements saying that government vendors are going to be required to comply with post-quantum cryptography, and you kind of have no choice but to move forward. So there's a huge market and a huge field open for this. And government is kind of a really good industry to start looking at, right? They have to be ahead of the curve. This is national security, critical infrastructure, like you all mentioned. That's kind of the next phase. Aerospace, defense, all these industries that have this sensitive data. This is going to be a very huge impact and a huge change that they're going to need to make. I mean, last time they had to upgrade to elliptic curve, it took 10 years, and we may or may not have that time.
No, that's exactly right. I mean, when it comes to data with future value, people need to obviously act within the time frame specified by, well, what's the duration of the forward value. And there are so many things that can reasonably be identified today that will have very long-term forward value, where people in the industry are just very clearly not giving a lot of thought to that prospect at all.
Yeah, I mean, if I had access to a quantum computer, the first thing I would do is try to take some Bitcoin, because there was a study that was done a few years ago now, like maybe 4 years ago, which estimated that a third of Bitcoin is held in private, it's basically keys that have been lost by the original owners, or accounts that are no longer used, dormant accounts. And so it's sort of like lost treasure. And many of those accounts are susceptible to quantum computer attacks because the people actually announce their public keys. And you can use Shor's discrete log algorithm to infer the private key from the public key information. So, that's an immediate way to make money if you had access to a quantum computer, which, wouldn't even have to be an enormous one. It could be of the size you mentioned of, 126,000 qubits is the best number we've seen for an estimate. And that could be very disruptive to certainly the cryptocurrency markets. And there is a lot of activity in that area to upgrade their systems. Yeah, Peter and I have co-authored a paper on looking at some of the economic consequences of cryptocurrency assets which are vulnerable to quantum computer attacks. And I guess you talked about that in a prior episode, right?
Yeah, there was, I post my wallet address on my website. So I was joking with folks that once that starts coming down or starts selling, that's when you should be worried. For now, I'm still okay with that. So that makes a lot of sense. So in this episode, we covered a little bit about the quantum computing revolution and the quantum threat, and stick around for new episodes about understanding more of the impact and the mitigation strategies. So just a closing thought from each of you. What message do you have for individuals and organizations who might be concerned about the looming quantum threat? What should be their next steps?
So I guess from my side, the thing that they should be thinking about is, one, work off the assumption that at some point in the future, quantum computers will exist and they'll compromise current day public key encryption. Secondly, what data do you possess that is at risk from that type of attack? And of that data, which one would be devastating if it were cracked 10, 20 years down the line? And if there is any non-zero answer to that question, then now's the time to start thinking about what can be done to future-proof that data.
Yeah, I would just add that, quantum computers were sometimes compared to fusion technology as a technology that would always be of the future. I don't think that's true anymore. I think people have come to more of a consensus now that we're likely to see quantum computing devices that'll actually have real practical applications by the 2030s and even the first half of the 2030s. You're seeing many companies now that are claiming that they will have 1 million qubits by the end of this decade. So that's enough to really disrupt security, cryptographic security. And since the payoff is so big, countries are going to push for it. And certainly there is a race with the two big players being China and the US. So I don't think it's I don't think anymore it can be just viewed as sort of an academic enterprise that you contemplate is something to worry about. I think it is absolutely time to get serious. There are several vendors now that are offering products which can enable you to upgrade systems to incorporate post-quantum cryptographic standards. NIST in the US has been running a standardization round for several years now, and they've picked some candidates which they believe are promising candidates. So the companies will have to use some of their own judgments on which kinds of protocols to use. Some of it's going to be based on concerns of how fast you want transactions to occur, how much security you want, how large of key sizes and so forth to work with. But, because we've seen such a massive improvement in classical communications with things like, Internet of Things and decentralized applications, these will have to also be made safe against quantum computer attacks. So I think it's important for companies to just get a look at the fields and start to make some investments. And we don't know the final answer. We don't know the best protocols to use yet, but I think the general advice is to do kind of a dual usage. So you would pick some kind of post-quantum cryptographic standard and couple it with some classical cryptographic standard, so you get some joint safety there, and in case one of them happens to be broken very easily. And certainly for governments, it's going to be absolutely essential to do this, because I think we often know that governments sometimes can move slowly. So, yeah.
Yeah, I was just reading the McKinsey report that came out in April saying China put in 15.4 billion government dollars into quantum technologies. EU is 8-something billion. US is 3.5. It's a lot of money going into it. And yeah, you're right. I actually saw Google started actually post-quantum cryptography experiments in the Chrome browser in 2016, I believe. And last month, I think they're releasing it now in the next versions of Chrome. So they're moving forward, even though it's not required yet.
Yeah, many companies are. Yep. No, there are lots of open standards already preemptively adopting it. Things like, I think, OpenSSH, the tunneling protocol, signal messaging protocol. Just the other day, they announced that being updated. So people are acting proactively.
Yes. TLS as well, I believe.
Oh, okay.
Anyway, thank you, Peter Gavin, for another illuminating discussion. Next time, we will continue bringing on new guests to the Quantum State podcast and discussions between us about mitigating the quantum threat, blockchain, and everything about quantum security. So make sure to subscribe on YouTube, Spotify, wherever you get your podcasts, and give us any feedback that you have on Twitter or LinkedIn. And we hope to see you next time.